Hello, everyone. So welcome to this seminar class of computer architecture. So today we are going to talk about processing memory in general. So we are going to start with some work that are actually two works that I did on my PhD about processing near memory and processing using memory. And then later on, actually in the middle, we're going to talk about seminar work that, if I'm not mistaken, IBM did some 10 years ago, 15 years ago, about process memory as well. So we are going to start with this work that Jean-Philippe is going to talk about. It's called DAMOV. It's a benchmark suite methodology for understanding data movement bottlenecks in applications and trying to correlate those with process memory. I'm not going to spoil much. So we have three presentations today, so let's try to be efficient. Jean-Philippe is a 7th semester computer science student here in ETH, and yeah, he's going to talk about this DAMOV work, so enjoy.
So yeah, hi everybody, and welcome to my presentation about DAMOV, a new methodology and benchmark suite for evaluating data movement bottlenecks. I'm first going to give you a brief outline of the talk. I'll start with an introduction and overview of the paper. Then I'll move on to data movement bottlenecks. I'll introduce the proposed methodology and touch upon the DAMOV benchmark suite. Then I will give you an example, talk briefly about the case studies presented in the paper. Then I'll give my conclusion over the paper, talk about the strengths and weaknesses, and then we'll have an open discussion. So for the introduction and overview of the paper, what is the problem? The problem is that data movements are a major bottleneck in modern systems. There's a lack of understanding about the key metrics to identify the sources for data movement bottlenecks. Also, it's unclear which is the most suitable mitigation technique for each type of data movement bottleneck. What are the goals of the paper? The goals are to find a way to identify the different causes of bottlenecks and correlate them to the best data movement bottleneck mitigation technique. Also, it compares memory and compute-centric architectures to do so. What is the approach? The approach is to look at many different applications, 345 to be precise, to find the key reasons for the data movement bottlenecks. What are the contributions? The contributions are a characterization of 77,000 functions and the 345 applications. Methodology to identify the types of bottlenecks present in an application and how different mitigation techniques might impact those bottlenecks. Obviously, the name-giving benchmark suite DAMOV, which is publicly available on the Safari GitHub, and the 4 case studies that highlight DAMOV's applicability. So let's talk about data movement bottlenecks. If you look at this very schematic visualization of a modern computer, you can see that everywhere where there are black arrows, data movement is happening. And the data movement bottlenecks discussed in the paper are due to poor data locality, insufficient memory bandwidth, and high average data access times. The one we've been looking at is a so-called compute-centric architecture. And data mitigation techniques for compute-centric architectures include deep cache hierarchies, aggressive prefetchers, and we conclude, or we will find in this talk, that those common mitigation techniques often fail with many modern applications. So I will now introduce a new architecture, the memory-centric architecture. One example of these are near data processing architectures, or for short NDP. And the mitigation techniques applied are, it moves the computation closer to the DRAM chip, it reduces the average memory access time, and has a higher DRAM bandwidth. The problem with memory-centric architectures is that, or no, not the problem. It has been shown that there are applications which profit from NDP systems, which include graph processing, machine learning, bioinformatics, databases, security, data manipulation, mobile workloads, etc. And now it has been shown, or it is unclear when memory-centric architectures will lead to significant speed up over CPU systems. To further solidify this statement, we will now look at different approaches to identify applications which suffer from data movement bottlenecks and also could take advantage from NDP. There are several approaches, but they're all not comprehensive enough. I will quickly go over two of them just so we get an understanding. The first one is the so-called roofline model, and the second one is the high last level cache misses per kilo instructions. So for the roofline model correlates the arithmetic intensity with the performance. And there are two regions we're interested in. The first one being below the so-called memory roof, and the second one being below the compute roof. It is said that applications which lie below the memory or the memory roof are memory bound and are deemed suitable for NDP, while applications which lie below the compute roof are deemed not suitable for NDP. We will now look at an example for this, or why this might not be the case. We have this analysis with the results for which functions are faster on a CPU or NDP system, where it depends or doesn't make a difference. And we can see that some of the functions get classified correctly. So for example, those functions are indeed memory bound and faster on an NDP system, while those blue functions are compute bound functions, which are also faster on a CPU system. But there are also functions which are classified wrongly, or it generally depends on whether it performs better on a CPU or NDP system. So we conclude that the roofline model does not accurately account for the NDP suitability of memory-bound applications. The second metric or model we are going to look at is the last level cache misses per kilo instructions model. It correlates the misses per kilo instructions with the NDP speed up over CPU systems. And again, there are two regions we're interested in. The first one being high misses per kilo instructions. This is defined by the authors as above 10 misses per kilo instructions. And the second region is low misses per kilo instructions. High misses per kilo instructions are deemed good candidates for NDP systems, while low misses per kilo instructions are not suitable for NDP. But again, we're going to see that this is only somewhat true. If we have a look at another analysis, we can see again that, yes, there are some applications which are correctly classified as NDP suitable and functions which are deemed to be faster on a CPU. But again, we find that there is a region which wrongly classifies the applications. So we again conclude that last level cache misses per kilo instructions do not accurately account for the NDP suitability of memory-bound applications. So coming back to our original statement that there exist no approaches which do so comprehensively, we now can conclude that no available methodology can comprehensively identify the data movement bottlenecks and also correlate them with the most suitable data movement mitigation mechanism. Now we'll have a look at the proposed methodology. What are the goals of the methodology? The proposed methodology should accurately classify the data movement bottlenecks, compare compute and memory-centric mitigation techniques, which I've introduced previously, and propose the suitable mitigation technique for each type of bottleneck we found. There are two main profiling strategies for memory behavior. The first one is architecture independent profiling, which is independent of the underlying hardware. And the second one being architecture dependent, which is obviously dependent on the underlying hardware. So let's have a brief overview of the methodology. So we'll start with some user input, which we then take and do some application profiling on it to find the region of interest. Then we'll look at the memory traces to do locality-based clustering, and we'll do a scalability analysis with some key metrics to do the final memory bottleneck classification, which then gives us some kind of decision tree to find the 6 memory bottleneck classes the authors landed on. Let's have a deeper look at step 1. So in step 1, the goal is to identify the functions in the applications that suffer from data movement bottlenecks. And the authors decided on a hardware profiling tool called the Intel vTune, which finds areas in where the CPU is stalled due to load and store instructions. And they called this metric memory bound. In the second step, we'll look at the memory traces. In this example, the temporal locality. Most of you have probably seen this in the digital design and computer architecture course. If not, this is a quick rundown. So for example, in this memory trace, we can see that the memory address A gets accessed 4 times. And then if we build a reuse profile histogram, we would, if we, for example, see this kind of pattern, increment the bin which corresponds to a memory address being accessed 4 times. So for example, if we look at this reuse profile histogram, we would say it has low temporal locality because memory addresses only get accessed a few times. While if we look at this reuse profile histogram, we would say it has high temporal locality because obviously memory addresses get accessed a lot of times. The second metric in the locality-based clustering is spatial locality. And again, I'll go briefly over it. So we're again looking at the memory trace. And this time we'll build a stride profile histogram. So in this particular example, we can see that the next memory address is being accessed. So we would increment the bin, which corresponds to the stride distance of 1. And for this particular stride profile histogram, we would say it has low spatial locality because the pattern is almost random. While, for example, this stride profile histogram has high spatial locality because the stride pattern is very linear and almost always the next or the second next memory address are being accessed. Next up, we'll do step 3. So we'll look at 3 key metrics defined by the authors, which we'll then use in the scalability analysis. The first one we've seen already in the roofline model. It's the arithmetic intensity. It's defined as the operations per L1 cache lines accessed. And it shows us the computational intensity per memory request. The second one we've also seen before. It's the last level cache misses per kilo instruction. And it's defined as the name suggests. And it shows us the memory intensity. Then the authors defined a novel metric called the last to first miss ratio, or LFMR. It's defined as the last level cache misses per L1 misses. And it shows us how much an application benefits from deep cache hierarchies. Next, we'll look at the scalability analysis, which is performed on those 3 key metrics. There are 3 different system configurations one is omitted in this picture. So the first configuration is a very standard CPU system with a private L1 and L2 cache and a shared L3 cache. And the second configuration is a private read-only L1 cache with no hardware prefetcher. The reason I'm mentioning the hardware prefetcher is because the third configuration, which is omitted, is basically the same as the so-called host CPU system, but also features a very simple hardware prefetcher on top of it. The scalability analysis we're doing is we're running those applications with a different amount of cores. So every core amount from 1 to 264 out of in-order and in-order host and NDP CPU cores is being run with a 3D stacked memory as the main memory. So now that we've looked at the benchmark suit, the methodology, I'll introduce the benchmark suit. So the authors started by analyzing 345 applications from different backgrounds and using the hardware profiler, they've only selected those functions which use up which use up more than 3% of the clock cycles and are memory bound above 30%. They found that this narrows it down to 144 functions out of the original 77,000. And from those 144 functions, the authors selected 44 functions on which they applied steps 2 and 3, and then selected the remaining 100 functions as validation set to see if the results they found are accurate. So let's continue down the path with the 44 functions on which step 2 and 3 are applied. So in step 2, we looked at the temporal and spatial locality, and we clustered the 44 functions using the k-means algorithm into 2 groups. The first one being the low locality group, and the second one being the high locality group. And it's worth noting that the closer a function is to the bottom left corner, the less likely it is to benefit from a deep cache hierarchy. Then we used the results from the scalability analysis. So from the last to first miss ratio, the misses per kilo instructions, and the arithmetic intensity to build this decision tree. And the authors landed on 6 memory bottleneck classes. The first one is called class 1A, which is deemed to be DRAM bandwidth bound. The second one is class 1B, which is DRAM latency bound. Third one is 1C L1, which is L1 and L2 cache capacity bound. The fourth one is class 2A, which is L3 cache contention bound. The fifth one is class 2B, which is L1 cache capacity bound. And the last one is deemed to be compute bound. And the authors correlated each of these 6 classes with a suitable data movement mitigation technique. So now that we've gone down the path of the 44 functions, we'll look at what we do with the remaining 100 functions. And we use these to validate our results. So first, we take those 4 metrics and with the 44 functions, calculate the thresholds. And then in a second phase, we calculate the accuracy using the remaining 100 functions, which gives us the accuracy to classifying functions in their respective data movement bottlenecks. It's found that the methodology classifies functions with an accuracy of 97% into one of the 6 memory bottleneck groups. And now we'll go over an example. So we'll look at the group 2A, which is L3 cache contention bound. So at or the class has high temporal locality and low misses per kilo instructions and arithmetic intensity, while the last to first miss ratio is increasing with the core count. So for the performance, the authors found that it performs relatively well on CPU systems at low core counts, while at high core counts, it runs into cache contention, which favors NDP systems. And we can verify that by looking at some graphs. For example, in the polybranch Gram-Schmidt function, we can see that above 64 core counts, the normalized performance rises significantly over the ones with a CPU system. Also, in the beginning, there are very low memory requests into the DRAM. As for energy efficiency, at low core counts, CPU systems are more energy efficient. This is due to the effective utilization of on-chip caches, while NDP provides large energy savings at high core counts. Again, we can verify this by looking at a graph. So again, for the lower core counts, we can see that the energy of the CPU system is quite low, while with high core counts, the NDP system performs much better energy-wise. So we conclude that for the class or the memory bottleneck class 2A, NDP systems can increase performance and save energy at high core counts, and thereby improve the scalability of applications at high core counts. Now for the case studies. So there are still many open questions related to NDP system designs. For example, how to design good interconnections for NDP systems, data mapping and allocation, NDP core design, offloading and granularity, programmability, coherence, system integration, etc. And the question those case studies try to answer is whether the DAMOV benchmark suite can be used to further study NDP system design. I'll just go briefly over these. So in the first one, the first study is about load balance and inter-vault communication on NDP systems. And it's found that only or a portion of the memory requests from an NDP core go into remote vaults, which increases the memory access latency for the NDP core. The second one looks at the differences between a CPU and NDP system with the same accelerators using functions from the methodology. And it's found that the NDP accelerator is faster than the compute-centric accelerator for class 1A and 1B, and slower for class 2C. The third case study is about different core models, so in order and out of order cores. And it's found that using in order cores limits performance of some applications, which results in static instruction scheduling cannot exploit the memory parallelism. The last case study is about fine-grained NDP offloading. And it's found that only a few basic blocks are responsible for most of the last level cache misses. So one could offload only such very basic blocks to an NDP system to improve performance quite a lot. For my conclusion, the paper introduces a very novel methodology for characterizing data movement bottlenecks. And in the process of this, it creates the DAMOV benchmark suite, which is the first open source benchmark suite for main memory data movement studies. It provides valuable insights into NDP system optimization and influences the design of efficient, scalable, and energy-efficient computing systems. Overall, it advances the understanding of data movement challenges, guiding future optimization efforts in computer systems. As for the strength of the paper introduces a very novel methodology and does so in a new way, which is by characterizing the 345 applications or 77,000 functions. And it does so in a very comprehensive and large-scale analysis. Which provides valuable insights for NDP systems. It also creates the publicly available DAMOV benchmark suite, which you can check out on the Safari GitHub. And because it's publicly available, it is very reproducible for everyone. So it can be used for future research. As for the weaknesses, the methodology tries to classify into six memory bottleneck groups, but it only covers very simple prefetchers. And as we've seen in previous talks, there are many more very complicated prefetchers. And one could argue that you can break those 6 classes further down to be more specific by looking at different types of prefetchers. Same goes for NDP system. So only a very simple NDP system is covered. Then data speculation in general is not really covered, which could also further break down those 6 groups. A very simple way of grouping those 6 groups is used. We'll touch up on this in the discussion part, but one could also argue that a more sophisticated method could lead to better or different results. The paper could also give more insights into the functions, and one could argue that the first 2 classes are kind of trivial. So if nobody has any questions at this point or any comments.
So I have a question for you.
Yeah.
You mentioned that only few basic blocks kind of data movement bottlenecks, right?
Mm-hmm.
Do you think it's possible to identify them at the beginning?
Can you repeat that? Yeah, sure. So in the case studies, right? Or here.
So you mentioned that only few basic blocks are responsible for LLC misses, right?
Mm-hmm.
So I'm asking you that, is it possible to identify them from the control data CDFG during the compile time? Is it possible?
I have to say I'm not really sure. Maybe one of the authors of the paper can answer.
Yeah, Gerald is here, of course.
Yes and no. You can identify basic blocks during compilation time, but this is a dynamic property, right? Cache miss that's going to be generated, which depends on the input set. So there are models that try to predict or emulate cache behavior during compilation. That is the LVMCA model, for example, from Sony, if I'm not mistaken. But it's a model, right? So it's faulty by definition. So this is why it's yes or no. Yes and no. Depends on the application, depends on how input set will change the behavior of the application.
Any other questions? Or otherwise, I would proceed to the discussion part. Okay. So I've briefly stated that a very simple method to group into the 6 memory bottleneck classes is used. It's the Euclidean and Manhattan distance measures. And now I want to know from you what other methodologies or practices could one use to find more distinct or accurate categorization results. So maybe think about, for example, machine learning or something like that.
So I saw that all these classifications happen only in 2 dimensions. So they plot arithmetic intensity against performance, or cache misses against performance or something, and maybe combining multiple of these metrics into more dimensions, like into 3 dimensions, we might see different clusterings. It would still employ the same distance, or you could maybe employ different distances, but it would maybe show different clusterings if we look at more dimensions.
Okay. Yeah, I agree. I'm not entirely sure whether this is not already the case. I can imagine that they've only been visualized this way, but yeah, this would be an idea. Anybody else? Or otherwise, I would proceed with the next question. So as for my next question, so far we've only been talking about hardware solutions, but there are many different software-related techniques to mitigate memory bottlenecks. Maybe you can tell me which one you would choose and why.
So I think optimized algorithms would be probably the best. If you can optimize algorithm, you should always do that. But obviously it's not always possible. For data compression, I would say it's probably not the best idea, because you always have to decompress it again, and it might only be relevant for really big data sets.
Okay. Yeah, I agree. Usually software-related solutions, or in particular optimizing your code, is much cheaper and can give you that extra few more performance. Anybody in favor of the hardware-related techniques?
Not any specific hardware-related technique, but I think many of these software-related techniques would go hand in hand with some kind of extra hardware. Like if we can add some kind of hardware to make the data compression easier or faster, it would make that a viable software technique.
Okay, yeah, I agree. Anybody else? So I'm probably a bit biased, but after reading the paper, I would obviously opt for NDP systems. So for my next question, which is about different data movements. So far, we've not looked at I/O data movement, network data movement, storage, and GPU data movement. So we've looked at a methodology which classifies data movement bottlenecks. How would you go about designing and analyzing different types of data movement bottlenecks, for example, from an I/O device or network, storage, and GPU devices? So I think in general, one could follow the same steps. So one would need to find a tool which returns regions of interest. So where data movement bottlenecks are occurring. And then one would define or need to define some metrics on which you can classify those data movements. So maybe if somebody can choose one and try to come up with a metric to classify the different types of data movement bottlenecks. Otherwise, I'd probably move on.
I guess, for example, for the GPU, usually if the GPU waits for the data, it doesn't do much. So you could measure the time it takes until it starts computing. That same goes probably for network, so you can measure the time.
Okay, yeah, that's a good idea. Anybody else? So yeah, then on top of those metrics, one could classify them using one of the algorithms we talked about. So for my next question, what do you think cloud computing architectures might do for data movement bottlenecks? Do you think they'd alleviate them or worsen them? And how could cloud computing service providers address these challenges?
So I think one obvious answer would be that it just moves the bottleneck from computing and data movement inside your own computer to the network. But I think like huge companies providing these cloud computing services have much bigger ability to build up their hardware or employ specific hardware accelerators to alleviate hardware data movement bottlenecks inside their own systems.
I agree. So cloud computing probably, yeah, as you said, shifts the bottleneck. Anybody else, maybe?
I think that cloud computing also allows you to choose a fitting system to your particular problem. So you're not limited to your own system, but you can kind of, depending on the program, decide which kind of system is more fitting for the issue.
Yeah, interesting. Yeah, I think so. This, or to summarize, you think this would alleviate some of the bottlenecks? because you can choose for example, if you know that for an application NDP works better, you can do
Well, yes.
NDP system.
Yes.
Okay. Yeah, I agree. Anybody else?
So if I think about a server farm, I would automatically think about websites and social media. And I think there's a lot of data movement happening over the internet. So I would feel like it would worsen the bottlenecks, because a lot of servers and cloud infrastructure are made to transport and broadcast data to a lot of devices and store them in the long term, more than our consumer devices in front of us.
Okay, so you would argue that it worsens the memory bottlenecks?
Yeah, just because there is way more data.
Okay.
And less computation.
Yeah, I agree. Cloud computing can output much more data than your normal PC. Anybody else? Otherwise, I would go on to my final question, which is how might emergent technologies such as quantum computing and AI algorithms, but not limited to these two, you can, for example, think about, 5G network or something else, influence future strategies for mitigating data movement bottlenecks?
Well, I think AI, for example, could be used to mitigate issues like, for example, cache locality. If you have like an AI algorithm that allows you to look at the behavior of a problem and see how the cache is used by the program, and then you can kind of adapt to the flow of the program and make the cache more optimized.
Yeah, this could be an interesting approach. Anybody else?
Going back to the clustering or classification of these different functions, we might be able to train an AI to better classify these different programs or functions to tell us from which architecture they would profit the most.
Yeah. Yes, I agree. That was something I was trying to get at in this discussion, but if it comes around in this question, it's also good. I agree. Anybody else?
Yeah, because you phrased it in a way that what influence future technologies might have. I'm going to turn your question around and wonder like what will change due to future technologies. So I think we will most likely see more hardware accelerators, and maybe that will give us a chance to have like more specific memory designs and memory hierarchies, or not hierarchies, or like direct access, depending on the specific workload that the accelerator has.
Mm-hmm. I'm not super familiar with that, but I think, yeah. So I think if there are no more questions, I'll end my presentation. Thank you for your participation, and thank you to my two mentors for guiding me. Yeah, thank you.
Is this on? Oh, yeah.
I'm happy to introduce our second speaker today, Eva. And Eva is in the third semester of her bachelor's degree in computer science, and she loves fashion, science fiction, and programming. Okay.
Thank you. Thank you very much. So good afternoon, everyone. Today, I'm excited to present an insightful paper titled Active Pages, a computational model for intelligent memory. This paper was presented at the International Symposium of Computer Architecture in 1998 and is therefore a rather old but still very significant paper. First, I will provide you with a brief executive summary, starting with the issue addressed by this paper, which is the ever-growing gap in performance between microprocessor and memory system due to the improvement rate of processor performance far exceeding the one of the memory system. The goal of this paper is to provide a model for an intelligent memory system which achieves way higher performance and thereby reduces the disparity between processor and memory performance. The key idea is that applications compute faster by shifting data-intensive computations to the memory system, to logic placed in the memory system. The paper even proposes a concrete implementation of this model by integrating FPGA logic and DRAM. As we will see, the results of the active page model are highly promising, achieving up to 1,000 times more speedup when compared to a conventional memory system. Now for the outline of my presentation, first I'll focus on the summary. Next, the strengths and weaknesses and the takeaways of my paper. I will address the takeaways of my paper. And lastly, lead a discussion centering around the impact of the paper almost 20 years later. So let's begin the summary by looking at the problem at hand. So the growing gap in performance between microprocessors and memory system is a well-known problem in the computing world and one most of you are already familiar with. As can be seen on the figure on the right, the performance gap had an especially strong incline in the 90s when this paper was first introduced, as it was and still is a major issue. Back then, there were already a lot of processor-centric optimizations to bridge this processor memory gap. But these approaches can lead to memory bandwidth problems. For example, prefetching algorithms might struggle to predict the actual access pattern, and this can lead to increased memory bandwidth usage without the provided results, without the provided benefits. So thereby, the authors of this paper didn't focus on a processor-centric view on this problem, but wanted to implement a model for an intelligent memory system called Active Pages. So Active Pages are a computational model which partitions applications to the memory system and the processor. The goal of this is to keep the processor running at higher speeds by offloading data manipulations to logic placed in the memory system. An active page consists of a page of data and associated functions that operate on that data. Yes, and now I would like to talk about the interface of active pages. So the most important part about the definition of the interface for active pages is that it's designed to resemble a conventional virtual memory interface. That means that we want active pages to be easily integratable with commodity microprocessors. Now, to give you a better understanding of the active page interface, let's look at an example of a sparse matrix multiply. So essentially, the code begins by calling ap_alloc to allocate a group of pages to store the matrices to be multiplied. Then AP functions are defined to include functions for index comparison and data gathering. Next, AP_bind is called to associate those functions to the previously allocated page as a pages. For a page to begin computation, the processor issues an ordinary memory write to an application-defined location. So the functions compute and write and gather their data to be multiplied. And as soon as they did that, they write to a set of synchronization variables indicating that the data is done. The processor continues by using this data and multiplying it and writing it back, etc. So now, having talked about the active page model, we're going to focus on the implementation of this model. So even though active pages can be implemented with a variety of different architectures and technologies, the focus of this paper lies on integrating FPGA logic and DRAM technology, here referred to as RADRAM. So an abstract figure of the RADRAM system can be seen on the right. As is depicted in the figure, the large DRAMs are divided into subarrays, each with its own address bits and decoders, and a block of logic associated to each subarray. Now to some numbers. The potential of gigabit densities became a real possibility at the time of the publication of the paper. So the paper introduces an good size for gigabit DRAMs to be 512 kilobytes. So as a size of the subarrays to be 512 kilobytes. The key idea is to divide, to associate half of the area of such a chip to logical elements, providing each subarray with roughly 256 LEs. Lastly, the processor specifies the interpage communication. Here, a processor-mediated approach is assumed, and we assume also infrequent communication. That means that when when an active page reaches a memory reference that cannot be satisfied by its local page, it blocks and asks the processor to satisfy this page by reading and writing to the appropriate page. So now we have talked about the active page model and the implementation, but still some issues remain. The paper specifies 3 such categories. The programming issues are closely related to the active page model, whereas the system and fabrication issues are related to the implementation, so the RADRAM system. Looking at the programming issues, we see that there are a lot of different topics that need addressing, but I will go through these rather quickly and only give the motivation and key takeaway. Starting with partitioning, the idea behind addressing this is to, the reason why we address partitioning is because we need efficient use of both the system, the memory system and the processor. Therefore, the key idea is to partition applications according to their complexities. For example, if we know we have a lot of complex computations and which only the processor can handle, we emphasize the utilization of the processor and use active pages only to provide enough useful data to the processor. On the other hand, if we know that an algorithm uses mostly integer arithmetic and data manipulations, We know it can be computed almost entirely within active pages. Consequently, we aim to optimize this by using as many active pages as possible and increasing the parallelism. Now to the next issue of programming, it's the activation time. So the motivation behind addressing this issue is to clarify that the majority of the time needed for to dispatch a work request to active pages is spent communicating to said page. That means that in this computational model, there is no need for additional data movement, or almost no need. Yes, we define activation time as the time it takes for a request to complete. Now, moving on to coordination. Coordination is crucial for the effective execution of computations in parallel. Even though I have talked about both interpage and processor page coordination, I want to highlight the key ideas again. So processor page coordination is done using synchronization variables, which act as synchronization channels between active pages and the processor. Interpage coordination, on the other hand, is done using memory references and is satisfied by the processor doing writing and reading to the appropriate page. Next up is the computational scaling. This is one of the most important issues and will be addressed again by the results. So the most important thing to remember with active pages is that the number of processing engines is coupled to the physical memory size, as opposed to traditional microprocessors where a fixed number of processing engines has to be applied on a variable problem size. That, coupled with the fact that many systems scale their memory size to the data requirements of an application, leads to a large number of active pages being available for parallel computing. So the actors, so this figure represents how the authors represent active pages to scale as data size grows. So here we can see two graphs. One is the speed up of the DRAM system when compared to a conventional memory system. The other is the time the processor spends waiting on an active page function to complete. So moving on to the first region of this figure, so which is the subpage region. Here we have relatively small problem sizes and therefore very little active pages with poor utilization, very little parallelism, and the activation time dominates. So it's no surprise that we have almost no speed up, and the time the processor spends waiting on the active page function to complete is a lot. But all of this changes when we reach the scalable region, where we see linear speedups. That is because when the problem size becomes large enough, the number of active pages scales linearly, and therefore so does the computational power. Yes, the next region is the saturated region, which is characterized by the non-overlap time becoming almost zero, as you can see here. This means that the processor is running at peak speed, which is great, but the number of active pages increases with data size, but the number of processors in the system won't. So therefore, the authors expect eventual leveling off of the speed up and even degradation as the coordination and synchronization cost dominates with the activation of more and more active pages. Moving on. I briefly want to give the key takeaway of data manipulation, which is that with did I do? Which is that active pages remove most of the burden of choosing a data structure. That is because most of the disadvantages of data structures can be eliminated in combination with active page functions. So this concludes the, hopefully, no? Okay, so this concludes the programming issues. I won't go into power consumption as a system issue into too much detail, and I would just want to give you the key takeaway, which is that the authors were conservative in their use of power and assume that were conservative in their use of power so that no power analysis has to be made. The same can be said for the fabrication issues concerning the merging of DRAMs and logic. While there exist processes to merge DRAM with logic rather well, the authors assumed penalties in logic speed and density. Moving on to the methodology of the paper, which is done using a three-step approach. First, a simulator was implemented which modeled the RDRAM system. Next, applications were chosen representing various algorithmic domains and a certain kind of partitioning. And lastly, these applications were implemented and optimized on a conventional memory system, then hand partitioned for an RDRAM system, and the needed active functions were coded into VHDL and synthesized to FPGA logic. Now let's look at these three steps a little closer. For the simulator, however, there's really not a lot to be said. The base environment of the simulation was the Simple Scalar v2.0 toolset. This environment was extended by replacing the conventional memory system with the RDRAM memory system. Moving on to something more interesting, the applications. To demonstrate efficient partitioning, a wide range of processor-centric and memory-centric partitioning applications were chosen. The key attributes of those applications are summarized in this table. I will focus on only two of them, which is the dynamic programming or the longest common subsequence for memory-centric partitioning, and the sparse matrix multiply for processor-centric partitioning. With that, let's get right into the algorithm of longest common subsequence. So this algorithm is representative of a broad class of string algorithms and can be found at the heart of computer algorithms to reconstruct DNA sequences. Most of you familiar with this algorithm will know that it's implemented using dynamic programming and runs in O of n squared for sequences of length n. However, these computations can be done in parallel as a wavefront starting in the upper left and ending in the lower right corner, as indicated by the pink arrows. This implementation of the algorithm runs in O of n log n for memory systems using active pages. Moving on to the opposite case, which is the sparse matrix multiply. We have already talked a little bit about the example of a sparse matrix multiply, and it's easy to see that it needs processor-centric partitioning due to the amount of complex computations involved. The key complex computation is the sparse vector-vector dot product, and therefore the authors provide an approach to do this implementation in the RDRAM system. As a comparison, in conventional implementations, the operation is done by the processor and starts by looking at fetching the indices corresponding to each non-zero element of both vectors in the dot product. Then it needs to determine which of these indices match. And after that, it needs to fetch the data corresponding to these indices. Then it multiplies it and writes it back. So several of these approaches use access memory and are therefore increase the memory bandwidth usage without providing without providing the performance benefits, because a lot of data is just zero. On the other hand, the REDRAM system implements a compute, gather, compare approach, which so the active pages fetch the indices and compare them. Then the data is gathered into cache line size blocks. The processor reads this compact data and begins multiplying it and writing it back. As you can see, only useful data travels between the memory and the processor, and that significantly reduces the memory bandwidth usage. For large enough matrices, we can find that the processor runs at peak speed because we utilize enough active page functions. Now to the last step of the three-step approach to evaluate active pages. So as I've explained earlier, the applications are implemented and hand-coded into VHDL and synthesized to FPGA logic. The results of the synthesized FPGA logic gives the authors information on how to design the REDRAM system. The key takeaway is that all of the applications can be done using the REDRAM system, since, as you can see, the number of LEEs used for each design is much lower than the 256 LEEs we assumed at the beginning. So now to the results. The applications were run on varying problem size. Here, the problem size is given in terms of the number of active pages, where each active page represents a 512 kilobyte super page. Two key observations can be made. First, that all of the applications execute better on the REDRAM system than they do on a conventional memory system. And the second observation that can be made is that the results scale as expected. That means that we have the sub-page region with small speedups. Then we have the scalable region with linear speedups. And we even have 4 applications that reach the saturated region. Here, the performance is limited by the progress of the processor and can even lead to degradation since the coordination cost dominates. It should be noted that every application would eventually reach the saturated region for large enough problem sizes. So looking at a different graph, which is the non-overlap time. So as I've explained earlier, the load the processor can handle is measured with the load the processor can handle is measured with the non-overlap time. So here again, the non-overlap time is given in together with the problem size. So 3 key observations can be made about this graph, which is first that the process-centric partitioning, the process-centric applications reach the complete memory processor memory overlap much faster than memory-centric partitioning. The second observation is that all of the 4 applications that reach the saturated region of speedup also reach a point of complete process memory overlap. And secondly, that applications like dynamic programming, which are largely memory-centric, lead to continue to have relative high percentages as data size grows. With everything we know so far, these results were rather expected. There's not a lot to be said about the cache effects, only that the execution time is largely unaffected by the size of the data cache. And therefore, I will skip this one. Next up is the partitioning. The partitioning of an application is analyzed with an analytic model, which was proposed by the authors. This analytic model represents an abstract application and is used to derive formulas to predict the performance of partitioning. Even though this application is largely simplified, we have the 4 key components, which is the activation time, the execution time of each active page, the time the processor spends waiting on active pages, and the post-processing time. With this model, we are able to obtain simple formulas to predict the performance, and balance the workload between processor memory systems accordingly to achieve maximum performance. The key takeaway is that the estimated speedups of the analytic model are extremely well correlated to the actual measured speedups of the simulation. This correlation can be seen by looking at the rightmost column of table 3. So now I would like to get to my conclusion. So the active page model does a great job at addressing the performance gap. The goal of designing a model to integrate well with commodity microprocessors is met. The active page model exploits the coming wave of technologies since gigabit densities, as well as RADRAM technology, were several years into the futures. And as I've said earlier, the performance of the RADRAM system is very, 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 very good, achieving up to 1,000 times the speed up when compared to conventional memory systems. Now I would like to get to the analysis of my paper. So the strengths and weaknesses first. The paper exhibits several notable strengths which contribute to its significance in the world of computer architecture. So one of its strengths is the introduction of the active page model as an innovative and forward-thinking idea to address the gap in performance. Furthermore, the clear and structured framework provided by active pages for the implementation is very good. It further facilitates the understanding of active pages and lays the groundwork for future practical implementations. The empirical data provided in the paper demonstrates the significant performance improvements. The results of the simple scalar simulator showcasing up to 1,000 times more speed up are quantifiable and are quantifiable evidence to the efficiency of active pages. Also, the exploration of sensitivity to implementations of other memory technologies is seen in this paper and is used to show the adaptability of active pages. So even though we have several strengths, the paper also has weaknesses which warrant consideration. So we have a limited discussion of the potential limitations and trade-offs involved in implementing the active page model. So while the paper focuses on the significant speedups achieved by the RDRAM system, it lacks an in-depth exploration of the trade-offs involved in integrating active page model with existing memory structures. So also the paper assumes infrequent interpage communication and therefore no additional performance overhead is, and therefore we have no additional performance overhead since no data is moved for an active page function to complete. However, the paper does not specify how this can be achieved and thereby ignores something that could very well lead to huge degradations in performance. Furthermore, there is nothing proposed on how to program and automate the partitioning, which is a very key aspect of active pages. Finally, the unrealistic assumptions that the processors only needed for the activation and the post computing is made, and it's very unrealistic since we have since the logic in the memory doesn't have direct access to the CPU structures, which are essential for memory operations, such as address translation and cache coherence hardware. So now I would like to conclude the paper analysis by giving you three things I found most impressive. So first, the paradigm shift of memory-centric computations. For the paradigm shift of the design of memory-centric computations implied by the active page model is very impressive due to potentially revolutionizing the way computational tasks are handled in the computing systems. Next, the amount of parallelism that can be achieved through active pages is really incredible, even more so when coupled with the fact the way the authors used the scaling of memory in combination with the already provided functions of active pages. Lastly, the idea to design the active page model so to be easily integratable with commodity microprocessor is a very good approach, since it offers a solution that leverage existing hardware infrastructures, making it easier to integrate them in the real world computing environments. With that, I conclude the analysis of my paper and would like to open my discussion if no further questions remain. So active pages is something now known as a processor in memory or a PIM system. At the time of the publication of the paper, a lot of systems were proposed centering around the idea to include logic in memory. However, they were all unsuccessful. And now that you have seen the active page model, can you think of reasons why back then the PIM systems such as active pages were not a success?
I'm guessing the the performance gap between memory and the processing was not that high in the 90s, and nowadays it's much higher. So that was probably a reason why it didn't take off as well.
Yeah, so I think you need to turn it on.
So I also think that the gap has widened since the paper was published. And additionally, there are more and more struggles with further advancing and minifying the processing nodes. So that might also make manufacturers seek new ways to improve performance further.
Yeah, so you have both answered why the systems are in use now again. So we have indeed a wider performance memory gap, and there are also a lot of other reasons, which I will show to you now. So essentially, there were several limitations back then. For example, is that me? So there were several limitations back then, such as that the applications that dominated were optimized for traditional von Neumann architectures, as well as integrating DRAM with logic was not easily achieved since it was limited by the available technology, etc. But now, as you have said, there are changes in the world of computer architectures which make PIM systems relevant again. For example, the increased importance of data-centric computing, also the necessity of PIM systems to sidestep the performance and energy bottleneck introduced by data movement. And now, since we have AI and machine learning workloads, we need architectures that can exploit, can work with a huge amount of data, which PIM systems can. And yeah, so, and obviously new technologies made PIM systems relevant again, such as 3D stacked DRAMs. So before we get to the next question, I would like to tell you a little bit about the PIM system nowadays. So as I've said, the 3D stacked DRAM is a major reason why PIM systems have renewed interest. The 3D stacked DRAM has much higher internal bandwidth than conventional memory systems, and due to these through silicon viases, which are essentially just columns connecting the different layers of the DRAM. In addition to that, we have most of the 3D stacked DRAM architectures propose an additional logic layer, which can communicate with both the processor and the DRAM. Now, because of that, now with that, new PIM systems exploit this model by integrating processing logic into the RADRAMs, into the logic layer at the bottom of the 3D stacked DRAMs, and try to exploit the high internal bandwidth. The processing logic introduced to this layer can vary from fixed function accelerators to in some simple in-order cores or reconfigurable logic. However, it needs to be said that the that highly sophisticated processors cannot be integrated into the logic layer due to manufacturing issues or better yet, the limitations of manufacturing technologies. So essentially, applications applications to exploit and interact with the PIM processing logic, the PIM systems expose an interface to the CPU. PIM systems typically, PIM processing logic typically is viewed as a coprocessor and executes only when code is launched by the CPU to that processing unit. Next, the granularity varies in the PIM system today, but that's not that important. And one thing that is important is that PIM systems now specify that compilers and programmers should mark the data and code as for execution in the PIM system. So now, having given you a brief overview of the new technologies and why PIM system is used again today, do you think that the active page computational model still has relevance in nowadays? And if so, do you think that it could be integrated with these technologies? So maybe think about what are the goals of active pages and if it's more useful now or if it's still not a success as back then. So essentially, I think that the active page model is very useful nowadays due to the fact that we have a lot more data-centric workloads, and the active page model exploits this rather well. Secondly, I think that the new PIM systems today and the active page model have similar approaches to the interface and therefore could be integrated with each other rather well. Furthermore, I think that introducing the 3D RAM logic into 3D stacked DRAM logic with the active pages could lead to higher computational power and therefore much higher parallelism. Yes, so I won't go into all of the details I listed here, but move on to my next question, which is if you can think of issues we had with the active page model, which are still relevant now. So to clarify, like the technologies and designs nowadays don't improve the active page model. Do you think that's true, or do you think that's true partially? Like, do you see some issues that still remain? Can you think about maybe things that I talked about in the weaknesses, and maybe look if they get solved by the 3D RAM technology or by the anything? So I think there are a lot of issues still not addressed. So I won't go into detail into all of them, but for example, we said that the active page model requires a new programming, that the active page model requires a new programming model. This is not great, as I've said in the weaknesses, since adapting to a new programming model is not that easy. And the PIM systems nowadays don't specify anything more except saying that, yeah, now we're going to leave it entirely to the compiler and the programmer. And yeah, so there are other issues like the lack of data mapping mechanisms. So to reduce the interpage communication, which I said could be become a huge performance overhead, we need good mechanisms for data mapping, which still don't exist in the new PIM designs. Yeah, so sorry. My last question would be if you have any ideas on how to solve some of them, that they don't have to be specific ideas, but maybe potential shifting in the programming in the computer architecture field, or
so maybe PIM systems could be used for first for highly specialized workloads. Because if we would do that, then we could do the data mapping according to the workloads that we already accounted for that. And it would drive up like program or like software that runs on the technology to like remove this hen and egg problem of like, because if there's no software, why would manufacturers build hardware for it? And if there is no hardware, then we can't write software for it.
Yes, that's true. That's a very good point, especially since PIM is nowadays only limited to specialized workloads. So that would be a good way to address data mapping. So I have proposed a lot of, some short-term solutions, but I would rather focus on the long-term solutions since, in my opinion, the PIM systems are the future due to the increasing amount of data we have and the performance of the optimizations of performance of processors becoming limited. And yeah, so the key thing I would propose is to focus on the manufacturing technology so that we can have highly sophisticated processors near in the logic layer. This would enable us to communicate less with the CPU, and therefore maybe even get rid of it entirely at some point. But I really think that optimizing for data for the manufacturing technology is important, since if we do that, we could also use some of the optimizations founded over the years for CPUs and integrate them into the memory system, making it decreasing the issues that still remain, since we have much more sophisticated designs. So with that, I would like to thank my mentors, Hayu and Shirai, and thank you all for your attention. And yeah, are there any questions? No, okay. So.
Hello, Giants.
Hello.
Hello. Could you please
Yeah.
share your slides on Zoom?
Okay. Yeah. Is it visible?
Yes, we can see them. We are trying to project them also, but they are visible on Zoom.
All right.
Can you show the presenter? No, I think it's okay.
Okay, I think it's fine. Are the slides too small for the students sitting in the back?
Hello, everyone again. Welcome to the last talk about SIMDRAM. So without further ado, I'm going to introduce Jayant. He's a first year master student at the ITSET department. He also did his undergrad in IIT Madras in India. And his major interests are in computer architecture, processing memory, and VLSI. And besides academics, he sketches and paints and also loves to cook. So please enjoy SIMDRAM, which is also some work that I did doing my PhD. And yeah, so please feel free to start.
Thank you for the introduction. So I'm Jayant, and I'd be presenting the work SIMDRAM, which is an end-to-end framework for bit serial SIMD computing in DRAM. I'll start with my agenda for the meet. So first, I'll discuss a brief executive summary of the work, and then we'll go into a little bit of background related to the work to understand the SIMDRAM framework better. And then we'll discuss about the SIMDRAM framework, its technical details, and about its system integration, and then methodology, how SIMDRAM is simulated and tested, and on what workloads. And then we'll look at the results that SIMDRAM offers, and then we'll go into the paper analysis and discussion. So yeah, starting with the summary. So first, we have the problem. So the current or the prior processing using memory techniques are limited to basic operations, and they only support functions like logical operations and additions, and they lack any flexibility to support new operations as needed. And they are also quite fixed or rigid, and furthermore, they require significant changes to the DRAM architecture, and which obviously comes with power and area overhead. So the goal of SIMDRAM is to design a comprehensive or an end-to-end framework for enabling in DRAM processing, and it enables complex operations to be performed within DRAM, and it is flexible, extensible, and programmable.
Excuse me, James, sorry to interrupt, but it seems that you are not advancing your slides. We are still seeing the title slide.
Oh, okay. Is it visible now?
Yes, now we see executive summary 1.
Yeah.
Okay,
sorry
cool.
about
Yeah,
that.
yeah. It's working now. Yeah, thanks.
Okay, so yeah, so as I was saying, it is flexible, extensible, and programmable, and the details about which we'll see in a couple of slides. And SIMDRAM also is enabled with very minimal changes to the DRAM architecture, so it doesn't pose a lot of overheads. And then, so yeah, to put it in a nutshell, SIMDRAM provides the programming interface, the instruction set architecture, the ISA, and the hardware support for using a massively parallel DRAM SIMD substrate. Coming to an overview of the results that SIMDRAM offers, it was shown to offer around 88 times and 6 times the throughput of a baseline multi-core CPU and a high-end GPU, and 257 times and 31 times the energy efficiency of them. And it was tested against 16 complex DRAM operations. It was also shown to provide 21 times and 2.1 times the speed up on over CPU and GPU over 7 real-world workloads. So coming into the much needed background to understand the key concepts of SIMDRAM. Why do we even need SIMDRAM in the first place? So as you might already know, it is due to the notorious memory vault problem. Data movement is still the biggest bottleneck in all modern computing systems, and more than 60% of systems' total energy consumption is from having to move large amounts of data from the processor, from the memory to the processor, and vice versa. And the computing units that are designed now, the CPU cores, GPUs, and accelerators.
Giant?
Yeah.
I'm sorry. We have to actually leave the room. Apparently, there is another meeting is happening. But we will continue the session over Zoom. So maybe you can pause your presentation for, let's say, 5 minutes, and then we will join over Zoom and you can continue.
Yeah, sure.
Sounds good?
Yeah.
Thank you. This for
that's mine.
okay. Good.
So it's okay to, should we keep the Zoom session alive here?
I think we should know because it's live streaming
okay.
here, I guess. So let me carry this. Somebody else. Okay.
Need to move this one back.
Okay, try to find is the interconnect lecture for one semester. Maybe it's like 19 or 20, something like that. It's really funny.
But like it's too awkward for all of the audience.
It's extremely awkward because the other professors like, for this to leave, my student should leave. And the student didn't know what to do because I was like, no, stay. And then
Let me have
I don't know what's so
Yeah. Jayant, can you hear me?
Yeah.
So I think you can resume your talk, but please start with, for example, on this slide to give some.
Should I start from the beginning of the slide?
Yeah, beginning of this slide sounds good to me. Yeah.
Okay.
Thank you.
Is it visible?
Yes, yes.
Okay. Okay. So coming to a little bit of background about before we go into the SIMDRAM work. So why do we even need SIMDRAM? So as you might already know, it is due to the notorious memory wall problem. Data movement is still the biggest bottleneck in all modern computing systems. And more than 60% of a system's total energy consumption is actually from having to move large amounts of data from the memory to the processor and vice versa. And the computing units that are designed now, CPUs, GPUs, and or even specialized accelerators, they are technically capable of processing data at much faster rates than the memory system can even provide data to them. So this is due to the limited memory bandwidth, which remains unexploited to its peak. And so, yeah, so in brief summary, we have a bandwidth limited and a power hungry memory channel between where the processing occurs and where the data resides. So traditional approaches in the past to tackle the memory wall problem were all processor-centric or compute-centric, which you're all aware about already, like using cache memories or multi-core processing, multi-threading, or parallel processing. So all of these compute-centric approaches just work to hide the bottleneck to improve the performance. But now there is a focus on data-centric or memory-centric architectures, that is processing where it makes sense, which is where the data resides in the system. For this, we have the concept of processing in memory. And it's divided into two categories. And we have processing near memory, where we add compute units closer to or within the DRAM subsystem. And this is popular with 3D stacked memories because they come with a logic layer, as we've seen in the previous presentation. And the other category is processing using memory, and this is what SIMDRAM is based on. And it uses analog operating principles of the DRAM circuitry itself to perform the computations, and thus it can inherently make use of the large internal bandwidth that DRAM banks have and the massive parallelism within the DRAM subarray. So coming to processing using memory, the prior works, as I just said, it uses the analog operating principles of the memory circuitry to perform computation. Thus, it can have a large internal bandwidth. So the prior works in processing using memory, or PUM, focused on performing bulk bitwise operations, that is performing bitwise operations on large DRAM rows at once. So these are operations like logical operations and or XOR, or slightly more complex operations like addition or multiplication. So now coming to the much needed background on how the main memory or the DRAM itself is organized. So this is how a DRAM is organized. We have a DRAM module or a DRAM DIMM. This consists of DRAM chips, and these chips consist of several DRAM banks, which are these 2D arrays of DRAM cells. And all of these DRAM cells are connected horizontally by a word line and vertically by a bit line, as shown in the figure. And these bit lines are connected to an array of sense amplifiers. So these sense amplifiers buffer, or the row, it's popularly called as a row buffer, basically latches the value that we read or write from and to the DRAM. And this is how a single DRAM cell looks like. It consists of an access transistor, which is an NMOS transistor. And the gate of the transistor is connected to the word line. And the source and drain of the transistor are connected to a storage capacitor, which basically stores the DRAM data as charge. and the bit line and the other end of the transistor is connected to the bit line. So now let's see how a single DRAM cell is operated. So operating a single DRAM cell, or the DRAM, basically has 3 commands, which are activate, read, write, and pre-charge. So coming to the activate, so to read a charge level in a single DRAM cell, the first thing that we do is we raise the word line. This basically enables the NMOS transistor. It connects, and therefore it connects the storage capacitor to the bit line. So what happens, and the bit line is usually typically pre-charged to a certain reference voltage, and typically it is logic high by 2, which is VDD by 2. Now what happens is the charge in the capacitor charge shares with the bit line, and there would be a deviation that would be induced on the bit line. And this deviation would be sensed by the sense amplifiers, and it would be amplified by the sense amplifiers. So in our case, we are reading a logic 1. So the bit line would be pulled by the sense amplifiers to logic high, and the charge in the capacitor would be restored as well. So now we have this value latched in the sense amplifier or the row buffer. And now all we have to do to read these values is to issue read or write commands to the DRAM bank, and the value latched in the row buffer could be read. And then to start another access to the DRAM bank, we basically disconnect the transistor, which basically disconnects the capacitor from the bit line. And then we pre-charge the bit line to the reference voltage, which is half VDD. And then we disable the sense amplifier. So this is how a single DRAM cell functions. And then now coming to one of the main techniques that SIMDRAM leverages, it's called a row clone. So row clone is a mechanism through which we can perform in DRAM row copy. So this is done by successively activating 2 rows. So by issuing an activate to row A and then to row B, as shown in the figure here, we will be able to copy the contents of row A into row B. So let's see how this actually works. We issue an activate command to row A first. So the storage capacitors in row A would now be connected to the corresponding bit lines, and then they will share with the bit line, and this will be sensed by the sense amplifier, and it will be amplified, and the bit line will be pulled to the respective values. And then after this, we immediately activate row B, which now connects the bit line to the storage capacitors of row B. So this will basically copy the charge on the bit line, or which is charged in row A, into row B, and which essentially is copying the data in row A to row B. And finally, as usual, a pre-charge is performed for the future accesses. And another important mechanism that SIMDRAM is based on is called triple row activation, or TRA. So as the name suggests, we basically activate 3 rows at once at the same time. And let's see what this leads to. So here, when we activate 3 rows simultaneously, we observe that the bit line would be pulled to VDD or logic high. So this is because out of the charges in the DRAM cells in row A, B, and C, the majority is logic high. So when they all charge share with the same bit line, the final deviation in the bit line would sway towards logic high, and this would be then sensed by the sense amplifier and amplified. And now all the 3 rows would be overwritten by logic high. So this operation is called the majority operation, because the final output that we get is based on what the majority values in all 3 of the rows. And so based on this TRA mechanism, the AMBIT was proposed. AMBIT implements in DRAM bulk bitwise operations, and it is one of these state-of-the-art processing using memory mechanisms. So by controlling the value in one of the rows in triple row activation, we can implement bitwise Boolean operations. So for example, if we tie one of the rows to all zeros, we would essentially be performing an AND operation, because A and B have to be high for the output to be high. And then when we tie one of the rows to all ones, we would essentially be performing an OR operation. So this way we can actually perform bulk bitwise operations within the DRAM subarray. And now for this to be logically complete, all we need is some way to implement the NOT operation as well. And let's see how this is done. So if we look closely into the sense amplifier construction, a sense amplifier is nothing but back-to-back connected inverters. So what Ambit does is it includes some specialized rows called dual contact cell rows. And these rows, into these rows, it basically feeds the negated value from the sense amplifier into these rows. So all you need to do to read the true or the negated value is to access these rows. So now that we have NOT and other Boolean operations that we can perform with the triple row activation mechanism, this is logically complete, and therefore, in principle, we would be able to perform any operation. Yeah, now a very brief overview of how a DRAM subarray organization should be for Ambit to be implemented. So we retain most of the rows in regular fashion, and we allocate only a few fixed compute rows for Ambit. So these compute rows will obviously need a special row decoder, which can perform triple row activation. And we also have two constant rows to store all zeros and all ones, as we saw it's needed for implementing Boolean operations, as we saw in the previous slides. So yeah, to summarize, we have seen the required background information to help us understand the SIMDRAM framework. So other prior works before SIMDRAM, which use processing using memory, as mentioned, only support basic operations and are not widely applicable because they lack any sort of flexibility. Also, they need significant changes to the DRAM subarray, which poses area and power overheads. Yeah, so coming to our focus work, which is the SIMDRAM framework, we will now discuss its key features and how the framework is designed. So as mentioned, SIMDRAM is an end-to-end, that is, it's a comprehensive framework for in DRAM processing. It gives us the programming interface, the instruction set architecture, and hardware support for efficiently implementing complex operations within the DRAM subarray. It is also flexible in that users can define their own operations and add it to the framework. And furthermore, it needs only minimal changes to the DRAM architecture. Yes, so the SIMDRAM's processing using memory substrate is based on two key features. The first one is the vertical data layout. So which basically is traditionally we would store data horizontally in a horizontal layout, but instead of in which all the bits of a particular data element would be stored in a single row. But in the vertical data layout, we would store, this is basically transposed. That is, each row would store the ith bit of multiple data elements. So this is done to perform bulk bitwise operations, as we just discussed in the previous slides. And also because this layout provides us or enables us to perform shift operation implicitly. Now with the vertical data layout, we can just perform a shift operation without needing any additional shifting circuitry, because row shifting would basically now translate to copying one row to another. And second feature is we have majority-based computation, as we just saw. And it was shown that implementing operations using majority was provided higher throughput, higher performance, and also better energy consumption, or better energy efficiency. Now coming to the design of SIMDRAM framework, there are three key steps involved in the framework. First, we generate an optimal majority or not-based and not-based implementation of the operation that we'd like to perform. And then in step two, we generate the sequence of DRAM commands which can perform our required operation. And in step three is basically how the sequence of DRAM commands that we just generated would be handled and executed at runtime. Yeah, so coming to step one, which is to implement an efficient majority or marge not implementation. Yeah, so the framework first performs a naive substitution, as we've seen before. We have these and or operations. By basically tying one of the rows to 0 or 1, we can implement and or Boolean logic functions. And so let us consider this circuit that we have on the left, which is basically a single bit carry out generator circuit, which takes in the bits that we are adding and the carry in, and it generates the carry out. So what the step one does is it first generates a naive implementation, merge not implementation, by just replacing all of the gates in the circuit on the left to majority gates. And this is an optimized circuit, and therefore we need to the framework needs to somehow optimize this. So in the next step, the framework optimizes this using a greedy optimization algorithm. And the details about this algorithm can be found in the paper cited below here. And then we move to step two, which generates the sequence of DRAM commands that are needed to perform our operation. So we call this sequence of DRAM commands as a microprogram, and each SIMDRAM operation is stored as a microprogram. So from the optimized match not implementation that we obtain from the step one of the framework, we generate the microprogram with the following steps. So our first task is allocating DRAM rows to the operands. And the second task is to generate the final microprogram, making sure that we maintain the correct flow of computation. Yeah, so to allocate rows to operands, the framework implements an allocation algorithm. And this algorithm considers two key constraints that we have. The first one, as discussed, is the limited availability of reserved compute rows with which we can perform DRAM in DRAM operations. And the second is the destructive nature of TRA. So when you perform triple row activation, we saw that all the three rows would be overwritten by the majority output. So these are the two constraints that are considered by the allocation algorithm, and it does the following. So it tries to assign as many number of inputs as possible to the available reserved compute rows. And then the rows that would be overwritten with the majority output from the triple row activation, the algorithm tries to reuse these rows as needed. Yeah. And from this, we generate the initial microprogram. So here we have the operands as A, B, and C in. So we need to allocate each of these operands to reserved compute rows that we have in the DRAM subarray organization. So we perform row copies with row clone, as we saw before, to copy row A, row B, and row C into the reserved compute rows. And then to actually obtain our output, which is C out, we need to perform the majority operation, which is performed with TRA. And then we will have the output over writing all of the three rows. And from this, we can copy it to a destination row. So this is what our initial microprogram would look like. And the framework now optimizes this. Yeah, so the optimization in the framework basically will merge successive row copies into one. And another optimization is to also merge a majority operation that is followed by a row copy. To explain how exactly this works, we will need to go deep into how SIMDRAM organizes the operand rows and so on. So for further details, you can actually check out the paper. It's quite interesting. So yeah, so after these optimizations, we will get our optimized microprogram. But this microprogram is for a single bit operation. So we need to extend this for n-bit operations. So we have a loop that repeats the microprogram for n times. So this gives us the final microprogram, and this is stored in a reserved DRAM region for future use, and so that we can use the programmer can use it anytime he needs it. And then the framework also adds a new instruction, which is denoted by bebop, to the instructions of the architecture. So the user can just use the bebop instruction to execute a SIMD operation. Now coming to the final step, we execute the microprogram that the framework created, and let's see how this is done. Yeah, so the SIMDRAM control unit is what takes the responsibility of executing the generated microprogram at runtime. So whenever the control unit receives or encounters a bebop instruction from the user input, as shown on the left here in the figure, it loads the corresponding microprogram which we've stored earlier in a reserved region in DRAM. And then it issues the sequence of DRAM commands that are required to perform this operation within the DRAM subarray. And because it's in DRAM processing, the final result would be produced within the main memory itself. And this is how a SIMDRAM control unit looks like. And again, this is very elaborate and intricate and requires careful explanation. So if you would like to know further details about it, it can be found in the paper. Yeah, moving on to how we integrate SIMDRAM framework into our systems. As we've seen, SIMDRAM operates on a vertical data layout, but the convention is horizontal data layout. That is, all the other system components would expect the data to be laid out horizontally. So SIMDRAM needs a data transposition unit that can transform or transpose data from vertical to horizontal and vice versa. So this data transposition unit was shown in the paper to have a low average impact on the latency, and it also comes with a minimal area overhead. And SIMDRAM also offers us ISA extensions, the bebop instructions, which the programmer can use to invoke in DRAM processing. And and there is no additional overhead in terms of address translation because SIMDRAM directly operates on physical addresses. And coming to cache coherence, so when there is shared data between CPU and the SIMDRAM enabled DRAM subarray, and if the CPU happens to modify the data, the programmer should actually manually flush the corresponding cache lines so that the SIMDRAM does not operate on invalid or stale data. So yeah, this is how SIMDRAM's data transposition unit is organized. So as shown here, it has 2 buffers and 2 units, basically, which can convert horizontally laid out data into vertical and also vice versa. Yeah, and with regards to the programming interface that SIMDRAM provides, we have 4 new ISA extensions. And as I said, these are represented by bebop. And first, we have the initialization instructions, which basically initialize the data that we want to operate on by transforming them into the vertical data layout so that we can use SIMDRAM operations to perform, to process them. And then we have 1 input and 2 input operations, these can be, and several operations can be augmented by the user himself or herself. And then we have predication instructions. These are used to implement the conditional if-else blocks. So to understand this better, let's see a quick example. So the C code shown here performs vector addition or subtraction based on some condition. So this is how it would be implemented using SIMDRAM operations. So let's take a closer look. So we first use the SIMDRAM object initialization instructions as we saw in the previous slide to transpose our data. That is the highlighted part shown here. And then we have addition from C code, which corresponds to SIMDRAM addition, which is the bebop_add addition here. And the same goes with subtraction. And then we have the bebop greater instruction to check for our condition. And then we have the bebop if else to conditionally execute addition or subtraction. So the C code shown above would translate into the this equivalent SIMDRAM code, which uses SIMDRAM operations. So this is how the same operation can be performed by the user by enabling the SIMDRAM operations. Yeah, so now let's look into the methodology, that is how the SIMDRAM framework is simulated and tested. SIMDRAM is implemented on the Gem5 simulator, and it is tested against Intel Skylake, which is a multi-core CPU, and NVIDIA Titan 5, which is a high-end GPU. And it is also tested against Ambit, which, as discussed, is a state-of-the-art processing using memory mechanism. And furthermore, the paper tests 3 configurations of SIMDRAM on 1 bank, 4 bank, and 16 banks. And each of these configurations provide different levels of SIMD, which are shown here. And for energy analysis, a tool called Cacti is used. And coming to the workloads on which SIMDRAM is evaluated, it's evaluated on 16 complex DRAM operations, which are listed here. And also it is tested on 7 real-world workloads that demand significant computing power, which are database workloads, machine learning and deep learning workloads, and image processing workloads. And now let's actually see how SIMDRAM performs. Yeah, coming to the results, we compare the throughput of all three SIMDRAM configurations against all three of our baselines, and we obtain these results. So this evidently shows that SIMDRAM outperforms all baselines across a wide range of operations. But if we see the comparison with GPU, we have lower performance for the one bank configuration. Can anyone probably guess why that could be? Okay, so this happens because of the bit serial nature that we implement that we implement SIMDRAM operations with. So when you implement operations like multiplication and division, it scales quadratically when we do it with SIMDRAM, and so that it scales quadratically and it worsens with the element size that we're operating on, and this is what leads to a lower throughput. And then coming to the energy efficiency, SIMDRAM beats all of the baselines and is highly energy efficient across all the 16 operations it was tested against. And this evidently shows how processing using memory mechanisms can improve energy efficiency by overcoming the memory wall problem. And on the 7 real-world workloads that we just saw, we can observe that SIMDRAM efficiently accelerates them and provides a good speed up against all of the baselines. Yeah, now coming to my analysis of the paper. Yeah, so the biggest strength of SIMDRAM is that it is the first work that provides such a comprehensive framework for in-DRAM processing mechanisms. Also, it only requires minimal modifications to the off-the-shelf DRAM chips, making it a really viable processing using memory framework. And it offers excellent energy benefits over all state-of-the-art baselines. And the paper discusses and implements SIMDRAM across all common data widths, 8-bit to 64-bit, using a massively parallel SIMDRAM substrate. Coming to a few more strengths, SIMDRAM framework also implements optimization without the programming needed, without the programmer intervention. And the paper elaborately discusses a wide range of challenges that will be encountered in system integration of SIMDRAM, or even for in-DRAM processing architectures in general. And it also discusses all the important overheads which would be involved in the integration of SIMDRAM, which support SIMDRAM's viability. So the paper elaborately discusses data movement overhead, data transposition overhead, and latency and area overhead. And lastly, it also provides elaborate comparisons against state-of-the-art baselines across all key metrics like throughput, latency, energy efficiency, etc. Coming to the weaknesses, we have the data layout conversion, which needs the data transposition unit, and that comes with area and power overhead and latency overhead. And this latency overhead was shown to worsen with the element size. It was shown that if we move from 8-bit computations to 64-bit computations, the latency due to the data transposition unit alone worsens by around 10 times. And we have the limited subarray size. So if SIMDRAM needs to operate on large amounts of data, it will need to have efficient mechanisms which would allow it to move data within the entire DRAM hierarchy. And this needs efficient and effective row copy mechanisms. And some of such works are actually described in the paper and were discussed in a greater detail in the paper. And SIMDRAM only supports integer and fixed point operations as of now. So there is no floating point support yet, which many data-intensive applications, especially scientific applications, would require. And because we are using the vertically laid out data, which can perform bit shifts with row copy, SIMDRAM cannot actually support complex bit shuffling or reduction operations. For this, we need a dedicated shifting circuitry. And then concurrent execution on SIMDRAM has not been implemented yet. That is, the SIMDRAM framework can now enable the execution of only one SIMDRAM instruction at a time. Coming to some more weaknesses that the paper discusses, we have the security aspect. Security is an important issue with SIMDRAM, and it was mentioned that it may increase vulnerability to the RowHammer attacks or the RowHammer disturbance. Also, reliability aspect, the reliability of the triple row activation or the TRA mechanism, which is key for SIMDRAM to function, worsens with the technology node size reduction, and it also changes rapidly with manufacturing process variations. Also, we just saw that SIMDRAM has an assembly-like programming model, which is not always easy or straightforward to implement, and hence it's something that is not quite favorable. And lastly, lastly, SIMDRAM provides a more than required level of SIMD parallelism, which I will elaborate in a moment. And lastly, SIMDRAM was only simulated, and the way it would perform on commercial DRAM chips is something that is yet to be tested. So yeah, as I mentioned, SIMDRAM provides more than the required level of SIMD level parallelism. So what exactly does this mean? So this plot is from one of the works in 2022, which is cited here below, and shows the iterations distribution in scalar loops of spec CPU 2017 applications, which are a standard for benchmarking CPUs. And these are some other plots from the same paper, which show iterations distributions in loops containing vector instructions of 128 and 256 bit widths. So from these, if we carefully observe these plots, we can actually see that the percentage of applications that need massive levels of SIMD parallelism are very limited, and SIMDRAM offers massive SIMD parallelism. So that could be redundant for many of the applications, for most of the real-world applications that we see here. So moving on to the discussion part, related to the limitations that we just discussed. So what do you think are some ways in which we can address the redundancy, by which I mean the massive parallelism that SIMDRAM offers? It's redundant for most real-world applications. Can you probably think of some ways in which we can address this redundancy?
So I have a point. So I think this redundancy can be used, for example, for better reliability. We can basically copy different application. I mean, different versions of that application, and have source of NMR or TMR. I don't know, and depending on how many copies of that. And basically, essentially, it can help better reliability, I guess.
Yeah, but that would come with energy overhead.
Exactly, I agree with that.
Yeah, so anything about how this redundancy can be addressed? Anyone?
Or you can design DRAM banks with smaller row sizes. I think it's already been done in the HBM. So yeah, maybe for DDR, the row size is too large. Yeah, the console is too redundant, then we can just reduce the row size.
Yeah, so that is one feasible method, and I think this already exists in modern DRAM architectures, where subarrays are actually divided into what are called as DRAM mats. So if we probably extend SIMDRAM to be enabled at a finer granularity, that is at a mat level, then probably the redundancy could be limited. Coming to the next discussion point, we also saw that the assembly-like programming model is not something that is favorable. So what kind of programming model do you think would be most apt for a framework like SIMDRAM?
So I cannot completely understand the question here, honestly.
Okay,
yeah, can you elaborate a bit more?
Yeah, so SIMDRAM now uses now makes the user to actually implement his instructions from the Boolean level, and then add them to the instructions set architecture, and then they have to be manually invoked in the code. So this is kind of cumbersome and not straightforward and sort of like assembly programming. So what changes could be made to this, or what would be an apt or an appropriate programming model for a processing using memory framework like SIMDRAM?
So my problem here is that assembly is not a programming model, but I guess some sort of automated compiler. I mean, compiler can make it automatic, generating the SIMDRAM instructions. So okay, that could be helpful, but I'm not sure.
Yeah.
How is it possible? So it's also a bit tough, I guess.
Yeah, to implement that would be harder, and I don't think that's been worked upon yet. Any other? Okay, so this was discussed in the paper. So SIMDRAM operations can be included within user space library routines. So this will basically ease the programmability, and it also would give the programmer a chance to transparently optimize the SIMDRAM execution. And another way would be using compiler assistance. So all compilers today have auto vectorization support. So probably something like this could be implemented for SIMDRAM as well. And another optimization that was discussed in the another programming model that was discussed in the paper would be something like composing groups of existing SIMD instructions into blocks that would match the size of a DRAM row and translating this into a single SIMDRAM operation. So, for example, Intel has the AVX extensions. So those can be used, and the compiler can actually group these AVX instructions into so that they fit within a DRAM row. That is, they operate on a total width of a DRAM row, and this can be translated into a single SIMDRAM operation. And such optimizations could be implemented within the compiler, and using compiler assistance could be a more apt programming model for frameworks like SIMDRAM. It will be hassle-free and easy to use. And yeah, the last discussion point, SIMDRAM was set to increase vulnerability to RowHammer attacks. So what could be some possible solutions or measures that we can take to mitigate or make it less worse?
Can you elaborate a bit more why it has effect on RowHammer?
I'm not entirely sure, but I think it's because of the multiple activations that we perform. Like row clone would require to copy our data to the compute rows would require a lot of activations, and triple row activations activate 3 rows at once. So this could actually create or like make the read disturbance phenomenon worse, and this could potentially make it more vulnerable to RowHammer. So what could be some?
Why do you think it will make read disturbance worse?
Sorry?
So why do you think let's say, triple row activation will make read disturbance worse?
I mean, in typical RowHammer, just activating a single row would cause the other rows to be disturbed. So now we are activating multiple rows at once. So probably the effect of it would be a little exaggerated, maybe.
Yeah, it could be, but it's not necessarily that the like the 3 rows involved in ambit or SIMDRAM operation.
Yeah.
Like they're not like always basically disturbing the same victim row, right?
Yeah.
Especially like if we have like the reserved rows. So
Yeah.
one of these rows will always activate in that region, and you know that in that region we always have fixed data. Yeah.
Okay. Yeah.
Yeah, but it's a good way of thinking that like, as we improve performance, we also need to think about security.
Yeah, I mean, probably when we are activating multiple rows at once, you could also think of it as making it easier for the attacker to actually attack rows nearby the POM enabled rows, because instead of him needing to issue multiple activations, if he actually makes use of SIMDRAM operations, which can follow a pattern in which you can actually have double-sided attacks or something, that could probably make it easier to launch a RowHammer attack. Yeah. So maybe that could be why it increases vulnerability. And so yeah, so the obvious answer is to integrate processing in memory approaches with RowHammer prevention and mitigation techniques. And some others are the allocation algorithms can try to alleviate this disturbance by suitably allocating the operand rows to make sure that a RowHammer attack could not be launched. And dynamic row refresh techniques specific to POM enabled DRAM subarrays could be used. Probably higher refresh rates when processing using memory is happening could be one way to prevent RowHammer from being launched. So yeah, that is it. If there are any more questions, I'd be happy to answer them. Or I can conclude the talk. All right. So yeah, that's all. I thank my mentors, Geraldo and Ismail, for their guidance, and thank you everyone for listening.
Thanks a lot, Jayan, for the excellent talk. Okay, thank you everyone for attending our today's seminar session, and we hope to see you all in the next week. Thank you.